Let's continue wave optics part 9. Last time we have seen the diffraction through a single slit. Slit A is reduced a little bit. We get the light like this and still smaller. When lambda is much greater than A, then the bending is still more. So here the plane wavefront does not bend if A is large. If it is little small, then visibly it bends, and if it is very small, then it acts as a point source of light. There are two classes of diffraction. The Fresnel's diffraction. Diffraction observed when the source of light lies at a finite distance from the slit. The screen is also at a finite distance. Fraunhofer diffraction. Diffraction takes place at a slit when a plane wavefront is incident on it and the wavelength emerging from the slit is also plane. So, both the source and the screen should be at infinite distance from the narrow slit. In laboratory, convex lens is used to get plane wavefront. Such a thing is often seen. Let us go from here to the lab and get the plane wavefronts in Fraunhofer diffraction. We have a cis lens. Two lenses are used here and a screen. Source S is at the focus of the first lens and that gives out plane wavefronts which passes through the second lens. But what happens is, rather than this entering the lens and emerging out at focus, what happens is these rays also bend and you have P0 and P. Now, where does this P come from? It is due to this diffraction of light. F is almost equal to D, since D is much greater than A. So, S is the monochromatic source of light of wavelength lambda placed at the principal focus of the lens YY dash. AB is a narrow slit of width A. The wavelets diffracted in the direction inclined at an angle theta with normal to the slit. They are brought to focus by lens MN at point P. Now let us see, a bright image is expected at the center of the screen. But we saw we get a diffraction pattern. That is a central maximum at the center O flanked by a number of dark and bright fringes called the secondary maxima and minima on either side of O. So according to Huygens' principle, when light falls on the slit, it becomes a source of secondary wavelets. If the aperture is small, a portion of light is bent passing through the aperture AB is diffracted in all directions, as we have seen earlier. Now let us draw the ray diagram. We have the lens, the rays of light enter from the source and this is the distance A of the width, slit width. So this will be A by 2, this will be A by 2 again. What is expected from this AB? This is the center O. There is a ray which comes out, it bends. This is not the normal path, but it diffracts and it comes to P. Let us draw a perpendicular AC. Now this BC will be the path length. This angle is theta, here theta. All these angles are theta. The wavelets from A and B will have a path difference of BC. If AN is normal to the diffracted beam, then in right angle triangle ACB, we have BC is equal to AB sine theta. So BC is A sine theta. If the optical path difference BC is lambda, theta 1 is theta, AB is equal to A, then what we have is lambda is equal to A sine theta. Such a point P is the position of the first secondary minima. If O is the midpoint of AB, then the optical path difference between the wavelets from A and O reaching the point P1 is lambda by 2. Similarly, path difference of the wavelets arriving at P0 is lambda by 2. Hence, the wavelets arriving at P from parts AO, OB of a plane wavefronts are out of phase. Therefore, the point P is of minimum intensity. That is, we have destructive interference. Now let's see minima, the equations. A sine theta 1 is lambda, we have seen. First minima at point P. The next minimum occurs at the point when A sine theta 3 is 2 lambda. In general, for the nth minimum, A sine theta n is equal to n lambda. Same can be applied to the other side of P0. Therefore, A sine theta n is equal to plus minus n lambda, n is equal to plus minus 1, plus minus 2, plus minus 3. Now let's see maximum. If Q is another point on the screen such that BC is 3 lambda by 2 and the angle theta is theta 2, then 3 lambda by 2 is equal to A sine theta 2. A sine theta 2 is 3 lambda by 2. This point will be the position of the first maximum. The next maximum occurs at theta 2. Q2, A sine theta 4 is 5 lambda by 2. In general, for the nth maximum, A sine theta n is equal to A n plus half lambda. A sine theta n is equal to plus minus n plus half lambda, where n is equal to plus minus 1, plus minus 2, plus minus 3, and so on. Now let us see the waveform for a diffraction pattern. So that's the intensity versus sine theta graph. This is the first minimum on both the sides and the first maximum on either side. Now these are the theta 1s and theta 2s. Minimum is A sine theta n is equal to plus minus n. N is equal to plus minus 1, plus minus 2, plus minus 3, and so on. For maxima, A sine theta n is equal to plus minus n plus half lambda. N is equal to plus minus 1, plus minus 2, plus minus 3, and so on. Distances of minima and maxima from the central bright point. So from the central bright point, we know capital D is much greater than A. Theta is very small. So sine theta can be written as tan theta. Theta is y by d. If y and d and y and b are the distances of the nth dark band or the minima and the bright or the maxima band from the central bright band, then theta is yn upon d, that is equal to n lambda by a. So y and d is equal to n lambda capital D upon a. So y and d is equal to nw. Theta is equal to y and b upon capital D, that is n plus half lambda by a. So y and b is equal to n plus half lambda d by a. So y and b is n plus half w. W is equal to lambda d by a. Similar to fringe width in interference except the central band and the reducing intensity on both the sides. Width of the central bright fringe. So let's see how to measure the width of the central fringe. Width of the central fringe is nothing but the distance between the centers of the first dark fringe on either sides. So we have width of the central bright fringe WC is equal to 2y1d, that is 2w, that is 2 lambda d upon a. This is the diffraction pattern for a single slit pattern. Now, if the slit is single, then this is the diffraction pattern. But now, if there are two slits, then two will have diffraction pattern, but there will be interference too. This is what we are going to talk next time. Thank you.